Okay, so in the previous video we did a quick overview of what had changed within Phase 3. In this particular video what I'd like to look at is the specifics of one of the instructions that was written, which is the JSR instruction. But just as a quick recap, on startup the accumulator is set to 9C, the program counter points to C000, and within the code we've set up C000, where is it here, to be a JSR with an absolute address here. So the absolute address points to B000, and B000 contains an RTS instruction. So all it does is jumps to the subroutine and then returns back from the subroutine. But that tests quite a few things, as we'll go through. Okay, so before we start, let's just prove that the code is in there. So C000F, for example, and there we can see that 200B0 is in there, which is good. The code works like this. So on startup, because we can either make it go from C000, or because the program counter is already pointing at C000, we can just type G, and in either case the program counter is pointing at C000, and from the fsm.c file the current instruction is sent into our array of functions, and our array of functions then decides that instruction points to here, as we described in a previous video. So the JSR function gets run, and the 20 of the JSR instruction gets passed in. Now in this case the 20 is not used, it doesn't matter, but we needed to pass it in because the function needs to be identical to the other functions. Anyway, so what happens? Well, once it's running that function, from the inst.c JSR, the program counter now equals C001, and that's because of this post increment here. So this double plus sign post increments that. So the CPU PC is passed in, and once it's passed in, the CPU PC is incremented. So at this stage the CPU program the program counter equals C001. Okay, and what we do then is we then say, well, go and fetch the current location of the program counter as the index into our memory array, and we know that it's C001. So inside of our memory array at C001, there it is, we have got 00, and that plays out very nicely by looking at it here as well. So it says in our memory dump C001 has nothing in it, as the value of 0 in it. What then happens, if we pull up our, there we go, what then happens is it copies that into the low part of temp, and then it increments the program counter. So the program counter now equals C002. This instruction starts to utilize some of the binary manipulation functions we've been discussing in the previous video. And what it says, and I've kind of put it into this description here, what it says is move this, so because everything's the right side of this equals, move this lot to the left by 8 bits, so make it here, and then OR it is the shortcut for OR with the value that's already in temp PC. Now the value that's already in temp PC is all 0, so it doesn't really matter, because I think in reality that X would actually equal 1 set to the compiler. I've actually noted that there. I think the compiler will probably set that to 1, because then it becomes 1 or the other, or both. And so in this particular instance then it would make the the temp PC equal the value, I think that was that B in there, equal that value, so then that would be B000. Then what it does, so now we've got our temporary PC pointing at where we want to jump to. So now what we have to do, the JSR instruction, what the JSR instruction will always do, and it will do this on a real 6502 obviously, is it will push the return address onto the stack. But there's a bug, and we'll come on to that in a second. But what it does is it now says, I'm going to push the contents of this onto this mouse, onto the CPU, onto the CPU stack, onto the memory stack. And because our stack pointer is pointing at FF, and let's make sure that it is, our stack pointer is pointing at FF. This instruction here, this instruction here says add FF there to the value of hex 100, which means 1 FF, and put the contents, the value of C0 in it. And because the current program counter is C002, so it takes the value that's in the program counter. I keep looking at the wrong line because I highlighted the wrong line. It takes the value that's in the program counter, shifts it right by 8, which is the opposite way around, so it moves the high byte into the low byte, and puts that into the stack. Then it does what's called a post decrement. And what a post decrement says is it will do the whole lot of this instruction on the current value of the stack pointer, and then once it's finished this, it will decrement the stack pointer. So at this stage now, the stack pointer, once it's finished doing that, the stack pointer will point to FE. Then it will copy the low byte of the CPU program counter into the stack, and yet again, once it's finished doing that, it will decrement the stack pointer, and therefore the stack pointer will point to FD, and therefore the stack will have two values in it, one at FF and one at FE. And lastly, what we then do is we copy the value that we put into the temp PC, because remember the temp PC was B000, which is where our subroutine runs from and where we want to jump to, and we copy that into the running PC, and that's what that line there does. Now we can demonstrate this. And if we say go, it should run the code from the program counter. So we say go, and wow. So let's have a look. There's our new registers, and as predicted, the stack pointer now equals FD, and the program counter is pointing at B000. Now if we do a memory dump, of the last part of the stack, what you'll notice is it's got C002 in it. Now that was predicted, but there's a slight issue, because if you look here, C002 is this memory location here, and this is the bug. Within the 6502, the original 6502 anyway, it didn't point to the instruction, the next instruction to be run, which was this one. Sorry, it wasn't this one, but it would have been the one after on C003, which there isn't one at the minute, but it would have been that. But instead, it points to the last part of the JSR. So the way that they got around that was the RTS instruction. That fixes the problem. So what happens in the RTS instruction is the RTS here takes the contents of memory at the stack, so it takes that bit of the stack, and notice the pre-increment on the stack there, and the pre-increment says increment the stack pointer before I do the instruction. There's the difference. So the stack pointer will now point to FE, which is right, because if we look at our stack again at the moment, right, have to change this mouse. At the moment, the stack pointer is pointing at FD, which is here, and there's nothing in it. So to actually do something with the stack, we do a pre-increment, so the stack pointer points to here with our value of 2. But we add the value of 1 to it to make it the right value, and the right value then points to the address after this one, which is correct, and that's exactly how the 6502 will do it as well. What then happens is we do a logical OR, there we go, and a combined left shift like we demonstrated before to push the next bit, which is the what did we do? Yes, so we do the pre-increment, so FF, so 1FF, it's the contents of 1FF here, the C0, into the high byte of the CPU program counter. So what happens is, if we now have a look at a memory address, if we do a dump on B000, we've got the value of 60 in the hex, and 60, as we know from experience, is an RTS instruction. That's a return from subroutine. So if we run that, it will return from our subroutine, and hopefully the stack pointer is now pointing to where it should be, and the program counter is pointing to the one after the instruction we've just executed, which is exactly right. Now, what other thing to notice though is that if we do a memory dump of the stack, or the last part of the stack again, notice that it hasn't cleared the stack, and that's normal behavior, because the CPU wouldn't do that either. Everything that you've got in the stack would remain in the stack, so you can't guarantee that the stack is always going to be 0. You've got to, if you want to manipulate it, you've got to manipulate it explicitly, because that's part of the that's by design. Okay, so the next instruction to look at is AND, because this one's quite straightforward really. And what we've got in our memory here, the one that we set up, we've actually got an AND absolute, and the AND absolute says take the value in B0 A0, and B0 A0 contains the value of AA. So take that value and AND it with whatever's in the accumulator, putting the value back into the accumulator. And the accumulator at the moment has the value of 9C. So if we go have a look, we clear that, and we go have a look at the value of 9C, 9C, and then we pull the binary up. There it is, 100111100. Okay, now if we then AND it with the value of AA, we know that AA is 10101010, because we demonstrated that in a previous video. We can predict quite clearly what would happen once we run this instruction here. So if we run the instruction at C010, so if we say go C010 and then show the registers again, we can see that it's ANDed it, and we've now got the value of 88.